Hi, everyone. My name is Christina Andonov. I'm Solutions Architect at AWS, and I help customers build platforms on Kubernetes.
Hello, everyone. My name is Apoorva Kulkarni. I'm also a specialist SA, Solutions Architect for Containers. I help customers of AWS adopt machine learning workloads on Kubernetes.
Let me take you back in time to the beginning of 2022, when almost nobody knew what ChatGPT was, and AI/ML was on no executive's priority list. At that time, business applications were the priority, and organizations had a platform team that created Kubernetes clusters, and application developers installed application on those clusters. And at that time, if you got hired as a data science engineer, and you went to that platform team and asked, can I have a Kubernetes cluster to run my ML workloads on? The answer usually was, sorry, can do. We have business applications to run. Instead, here are the keys to the kingdom. In other words, the keys to an AWS account. I'm sure you'll figure it out. And those keys don't look as nice as this one. They actually look like this. And at that time, if you were that data science engineer, you would start wondering and reconsidering your life choices and wondering, was that PhD really worth it? A few months pass by, and the company hires a few more data scientists. And they also hire an embedded DevOps engineer for your team. And life is better with company, and with everybody's help, you're able to run a couple of machine learning workloads in that account. But it's not easy, and still the question's like, was it worth it? And then, one day in November, that same year, everything changed. And now priority number one on every executive was AI/ML. And now that no can do turned into, let's see what we can do. So let's see what the platform team can do. They already built Kubernetes clusters for developers, and they also set up the add-ons on those clusters, including the tooling for developers to deploy business applications to those clusters. So now they would not start building clusters from scratch. They would actually reevaluate this platform that they already built, most likely in Terraform, to see how they can repurpose it for data scientists. And the first thing they should do in this case is go to the data scientist and ask, hey, what are you trying to do? What do you want to run? And the data scientist will say, well, actually, it's not one thing. I want to be able to run a variety of experiments. I want to be able to do data transformation and processing, inference, fine-tuning large language models, and I want to use this open source framework called Ray that is a Swiss Army knife when it comes to running Python workloads. Also, I want to be able to run multiple experiments at one time. So as a platform engineer, you can certainly install Ray Operator, and you can set up the tooling that the developers install the business application with for the data scientists a little differently, but they can, you can set it up so it installs a namespace for each experiment and stands up Ray cluster and JupyterHub. And then they can set as many namespaces as they need that way. So I know I brushed up on Ray Operator and Ray Cluster, and Apoorva is going to tell us a little bit more about Ray.
Yeah. So, show of hands, how many of you have heard of Ray or use Ray in some shape or form? Cool. So for the rest of you who are not familiar with Ray, Ray is a distributed, is a Python framework for running distributed applications at its core. And it has some higher-level libraries for you to be able to run training jobs or to be able to do fine-tuning, hyperparameter optimization. It has an inference capability through a library called RayServe. And because it was kind of born after the Kubernetes era, or it was kind of born during the same time out of UCB. They built it up, ground up, to be able to run on Kubernetes, which is great for us, right? So now we can run these Ray jobs and Ray clusters on top of Kubernetes. And the way it runs is there is a project called the Kubernetes operator, which is in the open source. A bunch of people from the Ray community came together to write it. And Kubernetes operator deploys 3 custom resources on Kubernetes clusters. So Ray cluster itself, then there is the Ray job to run ephemeral Ray clusters, and then there is Ray serve to be able to create an inference endpoint for serving real-time machine learning. So, and all of this obviously works across any Kubernetes environment, pretty much. And it's pretty easy to get it up and running in a quick start way. So you can just, it's a standard Helm chart deployment. You add the Helm repo and then Helm install the Kubernetes operator that deploys the CRDs on the cluster. And then after that, you can use the Helm chart for the Ray cluster, or you can create a YAML file. Either way, that basically provisions that Ray cluster on top of Kubernetes. The nice thing about that is these Ray clusters can live in individual namespaces. These are namespaced scoped, so you can create multiple Ray clusters across multiple namespaces. So you have the isolation boundary for that cluster to be able to consume resources within a specific namespace, adhere to the resource quota limitations and limit ranges and any security and governance policies that you have within the confines of that namespace. So a very convenient way to run these on top of Kubernetes. Back to Christina.
Okay, thanks. So now, as a data scientist, you have the means to get yourself a namespace and get Ray cluster and Jupyter Notebook in that namespace. But remember that platform was set to run business applications, and business applications usually run on CPUs. But to run ML workloads, you actually can't use CPUs. You need GPUs for that. And that just reminds me about the time when I spilled coffee on my keyboard, and I had my computer, but I couldn't really use it. I went down to the IT department and asked them, hey, can I have a keyboard? And they said, well, we don't have any in stock right now, but you can go search online, find one that you like, come back, tell us, and we'll get it to you in about 2 weeks. So I went online and I searched for a keyboard, and there was an overwhelming number of 698 choices. And I don't know about you, but when I see that, my brain goes, well, maybe I should get a really nice one, to serve me for the long run. So I checked the really nice ones, but then I don't want to lose my job either. So maybe I should settle for something in the middle. And then still remember, even if I get one, I still need to wait 2 weeks to actually get it. Wouldn't it be just nice if I could walk down the hall, swipe my badge, and get a keyboard of pre-curated number of choices that are safe for me, for the most part, and access my computer. So if you notice here, the pre-curated number of choices, well, sometimes I would actually need that really nice keyboard, but I don't need it for the whole entire month. I just might need it for an hour or 2. So now I have to start adding features to this vending machine. Also, while I'm at it and adding features, maybe I should expand the medium-sized keyboards to have more options and choices there, and just pick one that's available, or one that fits the best. So what would that look like in terms of the platform? How many of you here are using Cluster Autoscaler? Okay, 1, 2 people. Okay, so Cluster Autoscaler is how Kubernetes is. It's an open source project that you can add managed node groups, and it can scale those managed node groups. And it does speak CPU. You can also add managed node groups for GPUs to Cluster Autoscaler. However, what Cluster Autoscaler is not aware of is pricing. And here, remember that price tag? We need something that is very aware of the pricing. So to do that, we can replace cluster autoscaler with Carpenter. Carpenter is an AWS, it's a project that came from AWS. It is open source. It has been open source from the beginning, and it recently got donated to CNCF SIG autoscaling. So Carpenter, the differentiator factor here, why organizations choose Carpenter for running machine learning workloads is two things. First, Carpenter can bring up an instance in a matter of seconds versus a few minutes for cluster autoscaler. And as I mentioned, the other one is definitely price. Carpenter is aware of pricing, and I'll show you in a little bit how that works. Also, to make that cluster speak GPUs, you would need the NVIDIA device plugin, because the scheduler doesn't recognize the GPUs. So you install the NVIDIA device plugin, and it registers an nvidia.com/GPU type with the scheduler, so it starts recognizing the GPUs. All right, so we set up Carpenter, we give it some GPUs. If you are looking to move from cluster autoscaler to Carpenter, we're not going to cover that here. There is this talk happening at KubeCon EU next week on Tuesday. If you're going, attend it. It's going to be a great one. If not, watch the recording after. It's going to be okay. So let's go back to our vending machine and see how we can make Carpenter provide these sizes for us. So before we talk about sizes, let's talk about why we separated them in these categories. Because you could tell me, like, well, right now I can give all the instances to Carpenter. I can just have one size, and Carpenter should figure out the best price, right? It's aware of the pricing, so it should figure out the best price. Well, the difference why we separated in medium, large, and extra large is because the NVIDIA type. So data scientists would use a different NVIDIA type to run different workloads. For example, you can run like data transformation experiments or on A10G. You can run inference on H100 and maybe fine-tune large language models on A100s. Okay, so we know now why we have 3 different categories here. So for Carpenter, we're going to create 3 node pools, and you don't have to read all that. I'll explain it, don't worry. I know the back of the room can't see this here. So we'll have a node pool for each of these categories. And for the category, for the medium, we have 3 instance sizes. So Carpenter will select the best price depending on what we ask it to do. The other categories, however, we have 1 instance only. But if you notice here on the last line, we have a spot and on-demand. And usually the spot price is better, but sometimes the spot price will spike above the on-demand price, and that's when Carpenter would know it will pick the cheaper one. So we set 3 node pools, but we actually don't apply this to our cluster. What we're going to do with these YAML files is we're going to put them in a Helm chart. And we're going to put like a little if-else statement here with Helm. The top line is like if experiment size is medium or large or extra large. And don't worry, it will all make sense in just a moment. Okay, so now if I'm that data scientist, that YAML file that I'll create my namespace with looks like this. And it has an experiment size. So if I give it an experiment size, my tooling under the hood will know that I need to, it will create for me a node pool of size medium. Okay, you with me so far? All right, so while we're talking here and we're building this platform, the company hired a few more data scientists, and now we have a team B of data scientists as well. And they decide that at the exact same time we're running our experiment, they will also run an experiment of size medium. So now, via the tooling, they'll have another node pool of the same size. So how would the Ray cluster in Team A's namespace node to schedule that experiment on the first one, and Team B's on their node pool. Well, there is actually 3 ways you can do that with Carpenter. It's by matching the labels, by matching the annotations, or the good old taints and tolerations. So in this case, we're going to use taints and tolerations to do that, but you can use labels and annotations. So in this case, we put a taint on those, and we set the taint as experiment name, team-experiment, that's an arbitrary name that the team set. And then Ray cluster in the configuration will give it a toleration for that taint, and it will run the workload there. Okay. So now the screen is getting really crowded here, so we're going to send Team B on vacation for the time being. And just to reiterate, so now Team A gives this very nice snippet of YAML. I just want my experiment size. Here's the experiment name. And here's my team role. And it will create the namespace with the Carpenter node pool of the proper size. In this case, medium. So let's use now that setup to actually run, to see what happens when we run some workloads. Okay, so I can access the Jupyter notebook, and I will give it, in this case, I'll request 4 GPUs for my experiment. And let's take a look at those instances. 2 of those instances have 1 GPU each, and the 12 extra large has 4 GPUs. So also, one thing to mention here, in the Ray configuration, I have set resources, I have set limits. And how I want to set those limits is that this pod that will come up, I want it to fit in the smallest size in my group, but I want to leave some room in there for the daemon sets and things like that. So I'll kind of push it to the max, almost to the maximum memory in CPU, but not to the max. So that's why these settings. So now if I run this notebook, Carpenter, because I requested 4 GPUs, has a choice to, like it has many options, but one option would be to bring me 4 instances for 2 extra larges and fit 1 pod each, that's 4 GPUs. Or it will have a choice to bring a 12 extra large and to fit all 4 pods on that one. And it will do, again, that calculation based on pricing, spot, on demand, all the good things we talked about. So the great thing here is also that when we created the namespace and we put Jupyter Notebook and Ray cluster into that namespace, those are actually run on CPUs. Only the workloads, when I provide an experiment of size, when I run a notebook, then it brings up the pods, it runs its job, and then the pods go down. And even though I still have my node pool there, Carpenter will take those instances down. So I will not be paying for those GPUs. It's just, as the job finishes, Carpenter take down those pricey instances. All right. Okay, so let's go back to the vending machine, and now I have these, oh, sorry, I forgot to tell you one thing, the maximum replicas. If you set up Carpenter, so minimum is 0, of course, it can scale down to 0, but I should put some upper bound here so I don't do, guardrails. Good idea. In this case, 10. Okay, so let's go back to the vending machine now. So we have now all these nice features. We can use GPUs. We can bring up namespaces. It's going to select the proper cost-efficient way to do that. Well, that's great, but what if I need a USB drive? Can I get that? Well, let's go back now to the platform and see. I have this nice way of creating the namespace and Carpenter node pool. Let's see what it would take the current platform to create an S3 bucket. So first and foremost, that S3 bucket would need a few more resources than just an S3 bucket because we need Ray to be able to access it. And to set up access today, developers would just use Terraform. They would either open a ticket for the platform team, which would take another 2 weeks to turn around, or they would just go straight to Terraform. And let's see what that process would look like in Terraform. Well, they'll have to write something like this. And you don't have to read all that, but it is not straightforward. So some platform engineers have put all of these complexity in a module. And even if it's in a module, you still have to go and apply it to the account, wait for those resources to get created, grab the bucket name, which is straightforward, but then also get the role, which is not so straightforward if you're a developer or data scientist. Pass that into your Git repo. Possibly you know the proper location and the proper value in your YAML file to pass it, and redeploy your application. So that process is a lot different than what we're trying to get as a vending machine, that nice YAML. If I'm a data scientist, I don't even want to know that this bucket exists. I just want to use this. Remember that this is my interface, and I kind of like it so far. So what if I install a controller to extend the Kubernetes API in order to be able to create AWS resources? Currently, we have two options for that. One is called ACK, which stands for AWS Controllers for Kubernetes, and the other one is Crossplane. So I can install a controller to extend my API. Actually, the platform engineer will install that controller. You don't have to worry about it. And with that controller, with the namespace creation, you can set everything up for that S3 bucket to come and the proper permission, so you don't have to worry about like getting an S3 bucket. It would just happen automatically and get connected to your Ray cluster. Great. So we can get an USB drive now from the vending machine. But we've done all this work so far. So how about we put a cherry on top of it? What that means is the data scientist now has to use a Python library called Boto3 to access that S3 bucket. And Boto3 is OK, but how it writes files and reads files, it's not the best experience there. So we can make it a little nicer for developers, and we can actually mount that S3 bucket as a file system while we're at it. And we can do that with S3 mount point that came out November of last year at re:Invent. They announced it. OK, so now we have the vending machine. We have the cherry on top. And now we're actually going to show you how that works in practice.
This is a recorded demo, so I'm going to be pausing it if I need to explain something, or otherwise I'll keep it good. So just bear with me here. All right, where I'm starting from is a Kubernetes cluster. It's an EKS cluster, but it is Kubernetes. It's got some basic platform components already deployed on it. Right? So if you look at the list, right now it's Argo CD, which is going to be a way for me to pull down Git manifests and apply those Kubernetes manifests on my Kubernetes cluster. And there's a bunch of other daemon sets. But the one to notice is Carpenter, the NVIDIA device plugin, the S3 mount point, which Christina talked about, and the Kubernetes operator. So all of these are the building blocks of my data science platform. All right. It is, I think, a 2-node cluster, so all of these components right now are running across two instances in the node group. Right. So now let's take a look at going back to my UI. Right now, Argo CD is running, but it's empty. There's nothing running on it, right? It's waiting for applications to be provisioned. It's actually monitoring this repo. This is my vending machine, right? This is the repo where I will be asking my internal team members, data scientists, to open a pull request with that YAML file that Christina showed. And they will open a pull request with that YAML. I, as a platform engineer, can approve and merge that pull request or decline it, hopefully approve it. The idea is that this is the only interface that data scientists have to learn. They just have to know how to open a pull request and ask for what they want, right? So, oh, look, we already have 2 data scientists asking for Jupyter Notebook and Ray clusters. So we're going to merge a pull request from team A. They want to onboard themselves onto the platform. They give me an IAM ARN, which is the way they access AWS. Right? That's the role that was given to them by the cloud governance team or the cloud CCOE or whatever. They use that role to access AWS accounts, so they give me that role. And they tell me, my experiment size is a medium. I'm not doing much, but I still need an environment to do. Cool, let's merge that pull request. And now, when that request gets merged, Argo CD notices that there is a new environment that needs to be provisioned for this particular team. So in a few seconds, Argo CD will reconcile and start deploying that team's resources. And here we see Argo CD kind of creating that application. This is the app of apps, so to speak. So under this app, we have multiple Helm charts being deployed onto the cluster. And we'll get into that a little bit later, but you can see a bunch of resources are being provisioned. And all of those resources map to what Christina showed earlier with the diagram. It's the JupyterHub notebook, the Ray cluster, the S3 bucket, the IAM roles that need to be provisioned to access that S3 bucket. All of that complexity is completely abstracted away from the data scientists. They don't need to know all this is happening behind the scenes, right? They just open a pull request and we merge it for them. Cool. So now that these resources have been provisioned, remember, there's Carpenter running on this node, and we need to provision additional EC2 instances to be able to accommodate all those incoming pods. So Carpenter has noticed that these pods need to be provisioned. It goes ahead and provisions an EC2 instance type. And then once those instances are ready, we can see that in the team A's namespace, they will be scheduled on those newly provisioned instances. So all of this wiring is kind of what this vending machine is doing, right? So now that we have the environment up and running, we can now give the URL for JupyterHub to the data scientists, and they can log into their notebook instance. They didn't know what just happened for all of this to basically, just to give you a notebook, right? So they spin up the notebook, and we have some pre-curated notebook containers that they can use. These are approved notebook containers from IT and AppSec and whatever security governance controls you have. They use that notebook to be able to run their experiments. For my example, I'm running a simple data transformation job within the notebook. If you are a data scientist or have worked with notebooks before, this is probably going to look super trivial to you. For me, it was a lot of work to actually get it to work, but I'm pretty proud of it. Pip install a bunch of dependencies that I'm going to need to be able to run this experiment. After that, I'm going to be just creating some staging area for my data set to land, right? So I'm going to be pulling in a sample data set from the internet and from the public domain to run my experiment. And remember, we have S3 mount points now. So this mount point is being used as a file system within this notebook. So whenever I'm pulling down a large data set, it's going straight to my S3 bucket. I don't have to worry about AWS S3CP star.cv to like a bucket URL, right? I'm writing it to my local file system. I'm using PyArrow to read that iris.csv data set. It's a very like commonly used data set. It has data about flowers, their different lengths and widths. But what I want to do in my transformation is to calculate the area of those flowers or something like that. So I have the length and the width. I do a product of those, and that's the area. I want to add that area as a field inside that data set, the newly created transform data set. So this is what's happening in my transformation script. But I want to run this across a set of, in a distributed way using Ray cluster. I want to create a batch of this, chunk up the data, and have these Ray workers simultaneously work on these chunks of data. And then in my notebook, I'll gather all that data back and concatenate all of that into my transform data set. So that's the Ray script that basically does that job. I submit the job to the Ray cluster. The nice thing about Ray is that any dependencies that you need during the runtime of that script can be dynamically installed onto the Ray cluster using, just pass in an array of your pip dependencies, and Ray will dynamically just install those as it spins up. I've also copied my transformation, the Python script, to an S3 bucket, which gets mounted inside the Ray cluster as well. And remember, I'm just writing everything locally. I don't know that it's landing in an S3 bucket. It's just Ray that's just picking it up because it's the same bucket that's mounted inside the Ray cluster as well. I submit the job's going on, and now I'm just monitoring the progress of the job. With the simple loop, I can just keep pulling what's going on. It also forwards me the logs from like the jobs that are running, so if there's something going on that I need to take a look at. I have the logs in the notebook, but if I want to dive deeper, Ray dashboard is always handy. So I can open up the Ray dashboard within the browser, and if I want to deep dive into like if something went wrong, or if some logs are not showing up in the notebook, I can always do that. Remember Carpenter? Ray worker needs a node, an EC2 instance, to be able to run on. Carpenter has noticed that Ray worker needs to be provisioned. It needs an EC2 instance. It's a medium-sized experiment, which means it's going to run on CPUs. And so it's figured out that I can do this on a C6 X large instance, and that's what it thinks is their best choice at the moment. So it goes ahead and provisions that, and the Ray worker, the Ray autoscaler brings up the worker pod. The worker pod gets scheduled on that instance. It's up and running, and it's going to go ahead and finish that transformation job across those Ray workers that got provisioned. So the job succeeded. I can check the logs if I want to. If not, I can go back to my notebook instance, and I can test whether the job, the transformation actually happened the way I wanted it to happen, or do I need to run it again? So I need to, again, like concatenate all of those chunks that were performed by those individual workers into a single CSV file. And let's check. So yeah, it works. So the pedal area centimeter squares field was added to my newly transformed data set. So now that I'm able to, this basically is again, to call out that the newly transformed data set is also landing inside the S3 bucket as well. But I'm writing it locally on a file system. Just to prove that I'm not lying, it's inside the S3 bucket. So you can see the raw data set and the transform data set and all the partitions. Everything is inside the S3 bucket. So now if there are other jobs that need to, if there's a glue job that needs to take a look at it, or if there's something else, some other team that needs to access that data, it's already there. Right? We have one more team that we need to land onto the platform. And this time, this team B wants to do a batch inference using GPUs. So they've asked for GPU medium. Again, same config.yaml with the principal ARN and the size of the experiment. Merge that pull request. Now team B resources are going to get provisioned onto the cluster. Again, Argo CD controller reconciling, notices team B has landed, and starts provisioning the resources that team B needs inside team B's resources. Team A's resources are still there on the cluster, but they're left untouched. Team A is off to the races. Team B is spinning up. Same deal. It's the same cycle repeating itself, right? So we have pods landing into the cluster, Carpenter noticing that these pods need EC2 instances. Let me go figure out the best instance that I can get at this point in time, spot or on demand. And it's going to, once the instance is provisioned, Kubernetes scheduler provisions those pods onto the newly created instance for Team B. This time, Carpenter has chosen to do an M5 AX large because that's what it thinks is going to be the best choice. Remember the taints that we were discussing earlier? This is the Team B's taint, so no other workload that doesn't have the toleration for this taint can land inside this node. Team B's Jupyter Notebook, Ray cluster spinning up. It's the exact copy of Team A, but a more larger size, because they have asked for a larger size. And they're going to be charged for it. Looking inside the Ray cluster, just a sidebar here to see what Ray cluster looks like. There's a head group node and a worker pod. The head pod really doesn't do much other than maintaining the cluster membership and directing like the jobs themselves. It's the workers that do all the work. So we have, in this case, we have configured a max of 10 replicas, min of 0, so it has the ability to scale down to 0. If you need to keep a worker alive, just bump up the min replicas, desired replicas to whatever size you need. And we have resource limits defined per worker. So every worker gets a max of 7 CPUs, 30 gig of memory, and 1 GPU each. So if the data scientists need more than that, then they need to ask for a larger experiment size that they can work with. All right? And now the Ray autoscaler comes up. The data scientists can, again, from Team B, can go into the Jupyter Notebook. This time it's Christina. Notebook spins up. One thing to remember is we asked for a GPU instance types, and we're going to see like how that's being handled here. I'm using another notebook here for a prototype. This time, similar to the previous case, I need to install a bunch of dependencies. So same deal, like it's the Ray package, creating a staging area for my data set to land in. Again, it's the S3 file system. That's getting mounted inside the notebook. Maybe I can skip a little ahead. All right. So in this case, the Ray job that gets run is an image classifying job. So we're using an ML model that can classify a data set of images and add the score and the label on what it thinks is inside those images. But this job, according to this data scientist, according to Christina, needs at least 4 workers with a GPU each, which means there needs a total of 4 GPUs for it to run efficiently. After the predictions are being made, the batch predictions are done, I want to take a sample of those and just experiment with them inside my notebook, right? So this is what's happening. Basically take a sample, create a data frame out of it, stick that pandas data frame inside an S3 bucket, which I can then load up inside my notebook again. Submit the job. My code is in an S3 bucket again, which gets picked up by the Ray cluster, and dependencies as well for the script to run. I submit the job runs. I'll skip ahead. It's running. Now that the job has finished, I can test whether it's successful or not. So I can install pandas locally in my notebook, and check on it. Remember we said Carpenter takes those instances away? My experiment is done. I'm done with testing my data. And so I don't need those GPUs anymore. I don't need to manually shut them down. Carpenter knows there is no more workers running on those GPUs, and it's going to spin down those instances. It's similar to cluster autoscaler, but it's a little bit more quicker, and it's more smarter about how it's doing things. And with that, again, to prove that I wasn't lying, there's an S3 bucket with team B, and all of that data is in there. All right. I'll hand it back to Christina while you watch that. Thank you.
Yay, the demo worked.
Well, it was recorded. I cheated.
It's okay. That was an awesome demo. And if you notice, the first experiment ran in CPUs to be even more cost effective, which we didn't cover in the slides. And that's what the risk is when your co-speaker really likes to play with that stuff. So I think the first demo, there was a smaller model that would fit CPUs, so we added even like a smaller subset. Okay, let's get back to that. So now we have our vending machine. We know how it works. We have all the bells and whistles and the cherry on top here. And now if I'm that data scientist, and if you ask me, that PhD, totally worth it. All right, so if you want to find out more, we have data on EKS that has a lot of examples for Ray, Spark, and more. Go check it out. Trinium. And thank you so much.
There we go. All right. I'm going to steal this and run it for questions so we can get it on stream. Anyone have questions? Any comments?
My experience with JupyterHub and Python modules has been pretty time-consuming getting all the dependencies. And people I work with have resorted to VENV for compartmentalizing all the necessary modules they need. How does this deal with a dependency stream that might take 10 or 15 minutes or may even be impossible to resolve when you spin those up?
What was the tool you said?
VENV, virtual environments. Command line tool.
Okay, I'm not familiar with that. I don't have a good answer for you. I just say that most of the customers that we work with are in the camp of JupyterHub or Jupyter Notebooks. So your question is, how do you handle Python dependencies?
How does the product handle Python dependencies?
So this is not a product. We are suggesting a pattern that customers or any platform engineers can use to deploy data science-related components on top of Kubernetes to make it easier for data scientists to be able to do their jobs without dealing with the complexities of Kubernetes or a cloud provider. If there is some other tool that deals better with it, this pattern will work, hopefully, with that tool as well. This is not about handling software dependencies at the data science level. Like, we're not dealing with that issue at all.
I'm not too familiar with the S3 mounts, but I'm wondering how you handle bucket policies when, let's say, somebody wants to write data to a prefix they have no business writing data to. How do you handle, I guess, just permissioning when you mount that data locally?
So the question was, with that S3 bucket we mounted, regardless of the S3 mount point, with or without, how do we handle permissions to that bucket in this case? Because in the example we showed, that data scientist from the namespace would have access to everything in that bucket because it's a bucket per experiment. So we're spinning a new bucket per experiment. It could be set up to where you have a prefix per experiment. That would work too for a single bucket. In this case, we use the controller either ACK or Crossplane that wires up the URSA, which stands for IAM role for service account, or it can also do the new way of doing permissions, which is bot identity, in order to access the bucket or a prefix in the bucket. So the controller wouldn't just create a bucket. It would create the role, the policy, and it can also link, like it can take the bucket and put the bucket into the bucket ARN. And like if you design your controller API to do a prefix, you can even pass it a prefix. And then, let me just go back to that slide real quick here. It's gonna make more sense. Let's see. All right. There we go. So the controller will set this up for you. So it will set all the permissioning. It's gonna annotate the service account with the proper annotation, so it has access to the role. That will then assume the policy, and then we'll have access to the S3 bucket.
But your question is that you want them to have only some access to S3, right? Like here's, yeah, all of the teams are going to use the same bucket or something, and they all get their own prefix under that.
Yeah, that makes me feel safer.
Yes.
Yeah, so if you want that, you can set up the controller. So the controller has options, and depending on which controller you use, like for example, let's go with the example of Crossplane. Crossplane, you have the, like, when you install Crossplane, it comes with the S3 API. But then it has a construct called compositions and XRDs, with which you can build on top of that S3 API. You can build another API on top of your API. Does that make sense? And then your API can be specific. You can say, I can only pass in a role, and I can hard code my bucket name for this cluster, and I can pass it a prefix per experiment. And then it's going to come here, and it's going to set up your policy only for that bucket, only for that prefix.
Do you know how the new S3 volume mounts work with principals? Because at some level, my principal won't let me write. If I say I don't get to write to this prefix, and then I mount the file system with the S3 file system mount, does it show up for me? Is it just a read-only file system? I haven't played with the file system mount.
Yeah, if your principal does not have access to the S3 bucket, then you're not going to get it.
I can still mount the file system. I just won't be able to write to it, or maybe not even see it. And so that might be the best way, is just in your principal, when you mount that file system, just say, hey, this principal can't map to this prefix.
Yeah. Yeah. Does that answer your question? Yes. Okay.
Any other questions? All right, and I'm sure you'll both be around at least for a little while. I know you have to get out to Paris sometime soon.
We'll be around for the break.
But yeah, thank you so much.